In this video, we are comparing where we have 3 or more groups. And in this case, we're looking at what if there are different people in the group. So we have 3 groups, 3 different sets of people, and we can then look at, is there a difference in the categories that they classify themselves in which case we're going to use a chi-square test of independence. Are the 2 variables what group they're in, and the categories, are they related or are they separate from each other? If we have ordinal data, then we'll use the Kruskal Wallis test. And if we have ratio or interval data and it is normally distributed, then we'll use a one-way ANOVA. If we don't know what the distribution is, or if it's unknown, or if it's not normal, then we go with the Kruskal Wallis test. So let's look at these in our Python workbook. So just a reminder, we are working through drstephpowers.github.io/BIA, and we're working through this inferential statistics workbook. Click on it, goes to GitHub, open in Collab, go into your Google Drive, and of course, save a copy so that you can edit it. You'll also need the documents we're working for. We're working through our customer relationship management database dataset, CRM clean, which you can also find by clicking here on this inferential stats. All right, so let's go in. Difference between 3 or more groups. And so this here is where we have nominal data. So let's take a look at question 7 and question 23. And this is actually not from the CRM data set, but this is actually from the bargaining survey data set. So we're going to pull from that one. So just a reminder that here we have bargain numeric. This is the coded version of our bargaining survey from our previous videos. And we have imported that in and called it DF2. So let's go find where we were. All right, so we're going to do a chi-square test of independence, which means we're going to need to build a crosstab or pivot table, and we're going to need the chi-square contingency test. So from skippy.stats, import chi2 underscore contingency. From pandas, we're importing crosstab. And so we're going to build a crosstab here about question 7 and question 23 from the survey. So let's just remind ourselves. Question 23 was, what campus are you associated with? And so the members of our union could be at the North Campus, the South Campus, or the East Campus, 1, 2, and 3. And then question 7 said, in the last year, have you received any non-salary compensation? So we can see question 7 is nominal, right? Yes, no, I don't know. All right, so let's go to our data set. So we're going to first build a crosstab. And we are going to have the index be the question 7 and the columns be question 23. So let's load that in and take a look at that. DF2 underscore chi here. And so we can see question 7 had, if we go back just to check here, yes, no, and I don't know for the non-salary compensation. So here's yes, here's no, here's I don't know. And then question 23 was the north location, the south location, and the east location. So here you can see with this particular test, not only can we use 3 groups, the north, south, and east location, we can also have nominal data that is not just binary. It's not just yes, no. We have yes, no, and I don't know in this particular case. All right, to run the test, what we're going to do is we're going to enter in our crosstab, our frequency table. And so once you have this here, what it's looking for is that, are these numbers, do they look like they are random? Saying there's no relationship between question 7 and question 23? Or does the answer to one question kind of determine your answer to the other question? Is there a relationship? So we will just do chi2 underscore contingency. It's using a chi-square distribution. That's the CHI that we're referring to here. And then we just put in the name of our crosstab. So we do that here. We get a p-value of 0.169. And so what that is telling us, remember, p-value is less than our alpha. If we're using an alpha of 0.05, here the p-value is bigger than alpha. And so in this case, what we're saying is that there is no detectable difference, either because the sample size is too small or because there truly is no difference. So when we're looking at this here, there doesn't seem to be a relationship between question 23 and question 7. So how people answer question 7 doesn't seem to dictate how they answer question 23. So we're not detecting that there's this pattern to it. Let's take a look at another question. So that question 7 there was about non-salary compensation, but what about a question like, let's see, looking for another question that is part of a group. What about the question here in terms of, do you consider yourself to be part of an underrepresented group? So what we want to know here is those who identify as being part of an underrepresented group, are they equally distributed across the north, south, and east? Or does one location hire more underrepresented group individuals than others? So let's just go back into our data set here. And instead of question 7, let's look at question 22. So the rest of the process is the same. We build our crosstab. We can take a look at it here. And in this case, we also have 3 options for question 22. We have yes, no, and prefer not to answer. Then we can run the test. And what we get here is a p-value of 0.005. This is showing to us that there is a difference by location in terms of whether or not people are part of an underrepresented group. So there is a location here that doesn't hire. So remember, underrepresented group here is yes, no, prefer not to answer for question 22. So if we look at question 22, row 2 is no, and 3 is prefer not to answer. So notice that there are no prefer not to answers at the north location or the east location, only at the south location. Part of the reason for doing these tests is we are exploring the data. So perhaps there's something going on at the south location, which means that individuals who are part of underrepresented groups don't feel that they are safe in disclosing that information. So we're looking for flags, things that would lead us to investigate further. Perhaps there's something going on at the south location, right? This is north, this is south, this is east. That might signal there's something we need to investigate. Now the next test, so that was if we had nominal data, like yes, no, prefer not to answer. If we have ordinal data, then we're going to use the Kruskal Wallis. So let's just go back to, where is my table here? All right, somehow I have lost my decision tree table. So let's bring that back. All right, so 3 or more groups, different people in groups. Here we have, go down, we have our ordinal data, so we're using a Kruskal Wallis test. So let's take a look at how that works. To do Kruskal Wallis, we use skippy.stats and import Kruskal. With the Kruskal Wallis, we have here 3 or more groups. And so what we're going to do is we're actually going to create separate tables for group 1, 2, and 3 in this case. So we're going to take question 23, which is location, north, south, and east, and we're going to break it into a table that is the table that represents the people from the north location. We'll have a table from the people who represent the south location, and we'll have a table for the people who represent the east location. That's what this set of code is here. It is saying we're going to take the table DF2, and we are going to then subset it by finding just question 23 being equal to, remember, the double equal sign. So equal to 1, that's going to be our new table DF2 question 23A. And then we're going to create a second table, df2 underscore question 23b, which is just those who answered 2 to question 23. And then for C, we'll make a table that consists of those who answered 3 to question 23. So a north table, a south table, an east table. So then to do our Kruskal Wallis test, we simply call that information from each of those tables related to, in this case, an ordinal variable. So we're going to look at question 20. Question 20 says, do you agree with the following statement? My workplace is inclusive, and its Likert scale, strongly disagree to strongly agree. And so when we run the test, we're comparing the responses on that scale between the group that's at the north location, the south location, and the east location. So same question 20, but from the different data sets that we've created here. So we run that. Oh, Kruskal is not defined. Make sure you import your package, because if you don't have that package, that command does not work. So let's make sure we pull that. We get a p-value here of 0.001, less than our alpha of 0.05. And so this is telling us there is a difference in the 3 locations in terms of how people responded to question 20 about whether they believe that it is an inclusive work environment. Then we can do what's called a post hoc test. A post hoc test is a test after your test to get more information. So in this case, we found there's a difference between the 3 locations. The question becomes, which locations are different and which ones are not? So if you're doing a Kruskal Wallis, the post hoc test is called done. And to do this post hoc test, we're actually going to have to install a package into Python. It's not there automatically. We can't just call it up like we've been doing with our other packages. So we're actually going to need to do pip install. And then this is from SkyKit. We'll use that more as we get into machine learning. And then dash post hocs. So we need to install that. And then we can import it like we do our other packages once we've done that installation. So let's give that a moment. So then from SkyKit underscore post hocs, you can import the post hoc test called done. So that's what this is here. Okay. We're going to create a table, and that table is going to include our values from question 20 for those who are from the north location. So df2 underscore question 23a, question 20, basically just creating a table with the responses to question 20, 1 column for each location is what we're building here. And that's because this post hoc test, when you import the data to run the test, it just wants a table. It doesn't want you to specify in the command for the test the different variables. It wants it all together when it runs it. So we're going to do post hoc underscore done, and we're going to whatever we call that new table of information here. And then there's an adjustment. When it comes to these post hoc tests, there are different adjustments, and we'll see this later with another test, where there's different ways to deal with the fact that all of these tests are related to each other. And so the p-values actually have to be adjusted for the fact that there's this dependency between the tests. And so for this one, we're going to use home. There are others that you could look into. So if we run this here, what we find is we get a table, and this shows you, so 1 is going to be the north location, 2 is the south location, 3 is the east location. So of course on the diagonal, what we see here is all 1s because we're simply looking at the relationship between something and itself. We want to look at the off diagonal here is that we have the south location and the north location has an adjusted p-value of 0.001991, saying there is a difference between the north and the south location when it comes to question 20 about whether or not it's an inclusive environment. When we look at the relationship between location 1, the north, and location 3, the east, notice that p-value is greater than our alpha, or 0.05. There is no detectable difference here, either sample size, or there really is no difference in how they responded to that Likert scale question. You can see here, if we look at location 2, so that's the south, and 3, that's the east, we get a p-value, an adjusted p-value of 0.010598. If we're comparing to an alpha of 0.05, our p-value is less than our alpha of 0.05, and so there is a difference between the east location and the south location. We can explore this further by creating some cross tabs and looking at a bit more information in terms of how people did respond to this survey. So we can, from pandas, import our cross tab, and then we can also use matplotlib.pyplot. We'll call it PLT for short, allowing us to actually graph and show the difference in responses to this Likert scale question from the 3 different locations. So we see in our test that there is a difference. Now let's explore it a bit further in a table and a graph. So what we want to do is create a cross tab where we're looking at question 23 compared to question 20. We can just use our original data set here of DF2, and we want to turn it into percentages so we can compare, because perhaps we don't have the same number of people responding from the north, the south, the east. And so by normalizing it or turning into percentages, we can do a greater comparison. So give that cross tab a name. We're going to ultimately turn it into a chart, so we can call it here bar 23, since it's question 23 that's we're looking at. And then we can output it. That's what this tells you here. And we get a table. So what we see here, if we go back to our question 20, do you agree with the following statement? My workplace is inclusive. We had strongly disagree as 1, strongly agree as 5. And so then we can see at the north location, we have that 3 and 4 are the most popular responses. At the south location, notice that 2 and 3, so a bit more negative than the north location. And if you look at the east location, again, 3 and 4 are the most popular. And so that's why we could see when we did our test that there really wasn't a difference between 1 and 3. They're skewed a little bit more than the neutral. And whereas the south location is skewed towards the negative, giving us how the south location is statistically significantly different than the north and the east location. To see this on a graph, we can use a bar graph. We can use a horizontal stacked bar graph, and we'll look at this more in our data visualization videos. But to do a stacked bar graph, I'll just show you first what it looks like. So here you can see that it is stacked. So what we have is those who, if we go back to the question, we have strongly disagree, neither agree, strongly agree. All that information is stacked on top of each other into this bar graph. It is a horizontal bar graph. And what we've done is we have put it to 100% so that we can then see the more orange and red, the more negative the response, the more blues, the more positive response. So we can use the stacked bar graph to show at a quick glance that the south is more negative than the east and the north is a bit more positive than the east, but that could be just in the sample. It may not be statistically significantly different as we saw in our test. So how to create such a chart? We are going to plot, that's the matplotlib.pyplot as PLT. We will then take our crosstab. We are going to plot it. The kind is a horizontal bar graph. Stacked equals true. Our color map here, we're using red, yellow, blue. There's a number of default color schemes, and so you can explore alternative ones. And then we've set a figure size here just to make sure it's appropriately big. You could just leave that off and let it figure out itself. We're going to have a legend, and we're going to tell it where to locate it. So we're going to locate it here, and we're going to say lower left, and we're going to say number of columns equals 2. Oh, I don't know why I'm doing that twice. Let's remove that one because we don't want it to be the left and number of columns equal 2. What we actually want it to be is we want it to be centered. That's this B box to anchor that you see here. And the number of columns is actually 5. 1, 2, 3, 4, 5. If you make it 2, then it will do the first 2, and then it'll put the next 2 underneath it, and then the next 2 underneath that. So you're specifying how much is side by side and how much gets wrapped around. So we'd rather do here where we are going to put it centered. So what this tells you here is that this is in the center, and then this negative is that it is below the graph, and our number of columns equals 5. We're going to have our Y label, that's the vertical axis, say location. Our X label, that's the horizontal, say cumulative percentage. And then we're going to replace what it would put as 0, 1, 2 as the tick marks on the Y-axis. We're going to replace those with the labels north, south, east, so it's just easier to see. And we are going to put our labels of strongly disagree, 2, 3, 4, strongly agree, instead of the 1, 2, 3, 4, 5 that it is coded for in terms of this question, so that we can clearly see the strongly disagree on one end and the strongly agree on the other. So if we run this line of code, then that's how we get this graph that you see here. So we can create this visualization that supports the test that we did. If we looked just at the graph, it would show that perhaps the north is more positive than the east. We can see here the south is more negative. Our statistical test shows that the south is statistically significantly different, whereas the east and the north are not. Now, we have, as we're looking at these tests here, so let's just go back to our decision tree. We have 3 or more groups. We have different people in those groups. And here, if we have ratio or interval data, and we know that we have a normal distribution, then we have a one-way ANOVA. So let's look at the last of the 3 tests when we have 3 or more groups with different people in those groups. So we're going to do a one-way ANOVA. And to do a one-way ANOVA, we are going to use the command F_one-way. It comes from Skippy Stats, so we need to do from Skippy Stats import F1way, bring that in. And then we need to do just like we did before, is we need to create 2 separate tables, one for each of our groups. So here we're going to take our table DF2. And again, this is our collective bargaining survey, and it's the coded table, so it's all just numbers. And what we're going to do is we're going to create 2 tables, one for the north location, so that's we're going to take DF2, and we're going to look at just where question 23 equals 1. We're going to create a separate table just where question 23 equals 2, and a third table just where question 23 equals 3. Okay, so we're going to separate it out into 3 tables here. And then we're going to do our one-way ANOVA, and it is going to take that table for the north, DF2 underscore question 23A, and then we're going to drop the NA. So just in case that table contains empty information for question 17, then we want to get rid of that empty information. And we're going to do the same thing for location 2 and location 3. The one-way ANOVA really does not deal well with missing information, so we need to make sure that information is removed from our data set. And then we can do a comparison of question 17. And so let's just look what was question 17. Question 17 was, in the last month, how many hours of overtime have you worked? So is there a difference in the north, south, and east location in terms of the number of hours of overtime that people are working? Perhaps one location is utilizing overtime and another location simply hired more staff. So that's the comparison that we're doing here. And we enter that in. And we get a p-value here of 0.45, telling us that there is no discernible difference, either because the sample size is too small or because there really is no difference in overtime use between the 3 locations. If we had a p-value was less than 0.05, then we would use what is called the Tukey test, again a post hoc test, to determine where those differences lie. is the difference between the north and the south and the east and the north. So that's what the Tukey test would do. You only need to do it if you have a p-value that is less than your alpha. To do a Tukey, we do from Skippy.stats, we import Tukey HSD. And then in order to do the Tukey as a test, it does require a particular format, which means you need to give it a name. So here we just have res, results, equals, and then we do our Tukey test, so Tukey_HSD, and then we call question 17 from the north, from the south, from the east, again dropping any empty information, and then you print the results. And this will give you a table like this. Notice here these p-values, of course, are all large, and that is because there was no difference between the 3 locations, so we didn't even need to do this post hoc test. It would reveal the combinations that were significantly different. Your p-values there would be less than your alpha if there was a relationship. So 0 is the number it gives first, so 0 would be the north location, and then here we have 1 would be the south location, and 2 would be the east location. So it does the Python numbering of starting with 0, so 0, 1, 2, and shows you all the combinations. If we look at let's look at one where it is different, so you can see, if we are doing our customer relationship management data set, so DF3, we could look at, for example, the different salespeople. So perhaps we're going to create a table of just salesperson Taylor, salesperson Smith, and salesperson Zhao. And we will separate it out into 3 tables. And in this case, we could compare question 8 in the customer relationship database. So let's just look at question 8, average talking speed, words per minute. So again, we have to have a ratio or interval type data. And so here the talking speed is words per minute. So of course those are numbers. You can see here 46, 30, 36, 42 are examples of those talking speeds per minute. So again, from Skippy.stats, import our f_one-way to do our ANOVA. Create your 3 tables. So from DF3, that's the CRM data set. Create a table where question 1 is equal to Taylor, question 1 is equal to Smith, and a 3rd table where question 1 is equal to Zhao. Then perform our one-way ANOVA, calling each of those. If we don't have any missing information, we don't need that piece in there. We can run the test. In this case, you can see that p-value is very small. And so here we would use the Tukey post hoc test to figure out where the difference is. So we would make sure we have Tukey_HSD imported. And then again, we need to give a name to our Tukey_HSD that we are running and tell it to print the results of that in order to get it to output properly. So you can see here 0 and 2. So Taylor is 0, Smith is 1, Zhao is 2. And we can see that this p-value is small, so there is a difference in the talking speed of Taylor versus Zhao. There doesn't seem to be a statistically significant difference in the talking speed of Taylor versus Smith. And so if we look at then 1 and 2, we look at Smith versus Zhao, you can see that there is a statistically significant difference in terms of the talking speed here. So you can see no difference between Taylor and Smith, but a difference between all of them and salesperson Zhao. So with the Tukey post hoc test, we use it once we have done an ANOVA and we have found there is difference to figure out exactly where the difference can be found. We can show this visually with a graph. And so just as we're wrapping up our discussion here, we are going to create what is called a swarm plot. A swarm plot comes from Seaborn. There's a number of different data visualization packages we're going to look at in later videos. This one is the Seaborn package. To create your graph, you're going to need from Seaborn import swarm plot. And you're going to need to import matplotlib.pyplot as PLT if you haven't already. Then what we're going to do is call the command swarmplot, and the data is going to come from this DF3, the CRM data set. And what we want it to do is we want it to create a swarm plot using question 8 and question 1. You need to specify which one goes on the x-axis and which one goes on the y-axis. In this case, if we go back to our data set here, question 1 was the salesperson. Question 8 was the average talking speed. So we're going to put the average talking speed on the x-axis, so x equals Q8. And we want on the y-axis, on the vertical here, we want the names of our salespeople, so y equals Q1. Okay, and we'll put labels on these. So the X label is talking speed in March, and the Y label is the name of the salesperson. So if we run that, we create this graph here, which is a swarm plot. And so we can see, for example, that Smith and Garcia talk quite quickly, and Chen talks the slowest. Zhao, Mensa, and Devi have similar talking speeds in the middle range. And in our test we were comparing Taylor and Smith to Zhao, and you can see Taylor and Smith talk more quickly. They're kind of on this third group here compared to Zhao. So if we had chose 3 other people to compare, then depending on who we picked, we would see either no difference or a difference. So give it a try. Try 3 other individuals and run your one-way ANOVA. So instead of Taylor, Smith, and Zhao, try 3 other people. And do you see a difference? Then create your post hoc test if you do to figure out. And going back to our graph here, it should match what you're seeing on the graph. The added value of the statistical test is that it takes into consideration that this is just a sample of the overall data. And so it looks at how much variability there is, not just in terms of where it is on average.